Hey there, students. Let's see if we can try to understand how to go from the preliminary definition of a limit, which I've written here, to the formal definition of a limit, which is hard to understand for students initially. So in the preliminary definition of a limit, if we have the limit as x tends to a of f of x equals L written, so this would be for a particular function, for a particular L value, and for a particular A value. Then the meaning behind that preliminarily was that f of x can be made arbitrarily close to L when x is sufficiently close to A. The idea being that if the limit is 7 of some function, when x goes to 5, for example, that the function will get arbitrarily or infinitely close to 7 when you are plugging in x values sufficiently close to 5 or something like that. So this problem, the problem with this definition is this idea of the word arbitrarily close and sufficiently close. What does that mean? So that's why this is a preliminary definition. We talk about the idea of those things, but it's hard to specify what that means exactly. Those are fairly vague terms to have in a definition. So how can something be close to something else mathematically? So the first thing to remind ourselves is that L is some number like 7, f of x is some function like x squared, and then you plug into that function a values into the x squared function and you get close to 7, something like that. And when you plug into the function, you get an answer. So for example, if L is 7 and f of x is x squared, then when x is equal to 2 and I plug that into the function, I get 2 squared, which is 4. And then I could decide whether I thought 4 was close to 7 or not. So when you say f of x can be made arbitrarily close to L, we're talking about the number f of x gives you can get as close to some number like 7 as we want. So how do we measure whether one number is close to another number or not? We look at the absolute value of the difference between the two. So let's do that in blue. So if I wanted to, or maybe black, if I wanted to ask myself how close is f of x to L? So mathematically, how far apart these are is the absolute value of f of x minus L. That's the difference, size of the difference. So the size of the difference between the two is how close they are to each other. And so by saying that this can be made arbitrarily small, it means, or that f of x is arbitrarily close to L, means that the difference between them can be made arbitrarily small. And so arbitrarily small implies less than any given number. So the way we be more rigorous about describing that f of x can be made arbitrarily close to some number L is by saying that the difference between the two in absolute value can be made less than any given number. I can make f of x so arbitrarily close to L that no matter how small a number you give me, 1/10th, 100th, 1,000th, I can make it so that the absolute value of f of x minus L is less than that teeny little number you gave me. So the any given number part becomes crucial. Any given number. So what we're going to do is we're going to say let, and I'm going to use this big sort of E-looking thing called epsilon. It's a Greek letter. Let epsilon be any given number. So the idea is saying that f of x can be made arbitrarily close to L is the same as saying that the absolute value of f of x minus L is less than any given epsilon. You give me any epsilon, no matter how small, 1/billionth, 1/trillionth, I can make f of x closer to L than that. And the way I do that is by making x sufficiently close to A. So already it's probably a little hard to follow here, but this is the key to getting to the actual definition. So this this first part of the preliminary definition, f of x can be made arbitrarily close to L, this will translate to, given epsilon, the absolute value of f of x minus L is less than epsilon. That's what it means, arbitrarily close to L. So you give me how close it needs to be. You give me any number, no matter how small, let's call it epsilon. Then f of x minus L is less than epsilon. That means f of x has been made arbitrarily close to L. Now, the idea of a limit is that that's not always true. That's true when x is sufficiently close to A. So how can we communicate that? So let's move on here. So the idea for that part, now we have some space, is when is it that f of x minus L is less than epsilon? When x is sufficiently close to A. That means close enough to make that happen. And again, how do we determine closeness? When the absolute value of x minus A, that's how close x is to A, is small enough. So I'm translating x is sufficiently close to A as the difference between x and A is small enough to make f of x close to L, to make f of x minus L less than epsilon. So is small enough? Well, how small is that? That means there's some proximity, some distance between x and A that would be small enough to make that happen. And that's based on epsilon. You tell me epsilon, how close does f of x need to get to L? And I tell you how close x needs to get from A to make that happen. So that's going to lead to another definition. What is small enough? How much is small enough? So I'm going to say we let, and this is kind of a Greek D, delta. Let delta be the number that is small enough. So the idea is we have some arbitrarily chosen epsilon, which is the proximity that f of x needs to get to L. 1/10th, 1/billionth, 1/trillionth, some number we expect to be small to show that f of x is tending to L. And once we are given this number, then we can determine how close x needs to get to A to make that happen. We can tell what sufficiently close to A means, and that number of how close you need to get to A we're going to call delta. So we are given a small epsilon, then we find a small enough delta. So delta is chosen in response to epsilon. How close do you need me to get to L? Oh, okay. Here's how close x needs to get to A to make that happen. You give me an epsilon, I choose a delta. So you may be completely lost at this point, but I'm going to now take a stab at writing the actual formal definition and see if it hopefully has a better chance of making sense after this discussion than it would right out the gate. So let's take a look here. So here's the formal definition. And again, this is the definition of the same thing. This is the definition of a limit. So what was the thing that we read up before? So we are defining what's in the red box here. The limit as x tends to a of f of x equals L means formally that for any epsilon greater than 0, and this is a number that we expect to be a very small number because it's saying how close to L f of x needs to get, but it's arbitrary, so it could be true for any number no matter how small, 1 billionth, 1 trillionth. There exists a delta greater than 0, and again, we expect that will be small because that's how close x needs to get to A to make f of x close to L. It's in response to the proximity that f of x needs to be within L. So you give me epsilon, then there exists a delta. There's this number small enough for delta such that when 0 is less than the absolute value of x minus a is less than delta. So what does that mean? That means when x is sufficiently close to a, and what is sufficiently close? Where the difference between x minus a is less than delta. Delta is the number that says how close x needs to get to a. So when x does get that close to a, without necessarily being a, that's why the difference is greater than 0. When x minus a has an absolute value less than that delta value, then that forces f of x to be close to L, and the way we write that is that then that means that the absolute value of f of x minus L is less than epsilon. That's it. So the idea, it's hard to read with these Greek letters and everything, but the idea is that we want to claim that as x gets close to a, f of x gets close to L, and these are infinitely close. And the preliminary definition was that f of x can be made arbitrarily close to L, meaning closer than any number, which we're now going to call epsilon. And that can be made to be true when x is sufficiently close to a. And how close is sufficiently? We're calling that number delta. So the definition would then say for any epsilon greater than 0, and the implication is no matter how small that is, there exists a delta greater than 0, and the suggestion is that that will be very small in response to epsilon, such that whenever x minus a is less than delta, when x is close enough to a, less than that sufficiently small number, then that forces the difference between f of x and L to be less than epsilon. So that's a lot to think through. It's definitely usually more than you're used to dealing with in terms of logic and strange notation. Try to think it through. Try to discuss it. I suggest students try to discuss these things with each other to help the ideas take hold or sink in. And please, of course, ask me all the questions you need to, both in office hours and even in class when we need to. So keep up the hard work. Try to look at this hard. Try not to hurt your brain, and best of luck.